Welcome everybody, my name is Nemeth Gabor and the title of my presentation is Experimental and Numerical Investigations on Steel-Concrete Interaction of Embedded Corrugated Web Composite Members. So first, I will shortly introduce the topic of this presentation. Then I will talk about the push-out series carried out on our department, then the process of numerical modeling. Then I will present the results, both the experimental and numerical investigations. Then I will shortly summarize the presentation. So, trapezoidal corrugated profiles are been around since decades in building construction, but they only started to use it in the 80s in bridge construction because of its advantageous behaviors. For example, greater transfer stiffness and greater local and global buckling resistance. The first bridge which has corrugated steel web is the Cognac Bridge in France. At the end of the 90s, in Japan, they built the Hondani Bridge, which has embedded steel web directly embedded in the concrete slab, and also the bridge has closed cutouts as shear connectors, which led to further advantages because with the absence of top steel flange and the headed studs, the welded structural elements are decreased, which is a really advantageous thing from a fatigue point of view. At our department, our goal was to investigate and develop similar designed prefabricated hybrid beams, and for this step was to analyze these kind of shear connectors. So as you can see, this push-out specimen doesn't look like a standardized one in Eurocode because of the embedded design. So there's an eccentricity because the load is acting here, and because of this eccentricity, unfortunately, there's an undesired bending moment, but we can exclude this effect by placing steel rods at the bottom of the specimens. In this presentation, I will present 8 results of 8 specimens with 4 different fold geometries. I will show you specimens with 30, 45 and 60 degrees inclination angle, and also with longer 200 millimeter plate width and shorter 100 millimeter plate width. Also, the embedding depth will change from 100 to 125 to 150 millimeters. So altogether, we carried out 57 push-out tests, and as I mentioned, I will introduce 8 of them. All of them will be so-called reference specimens, which means there will be no additional shear connectors between the concrete and the steel. The only connector will be the trapezoidal profile itself, which is embedded directly to the concrete. Here you can see a picture of the experimental layout. We measured the slip between the 2 materials on both sides and the displacement in the middle. The numerical modeling was performed in Athena software environment. we used volume elements, and here at the right you can see a stress distribution figure where you can see that the load transfer happens mainly under the inclined angles. So the displacement load acts here. So the steel part moves downward, and the concrete gets the load by the interface elements between the two materials. We observed two kind of failure modes during the experiments. The first was when the concrete slab just opened without any kind of cracks or crumbling on its surface. And the second one was when the concrete slab crumbled and there was no opening almost at all. So the explanation that the load transfer happens under the inclined angles. So the force on the which acts on the concrete is angled as well, and this angled force can be divided into two components. The horizontal one causes transverse bending, which leads to the slab opening, and the vertical one, the vertical component, causes concrete crumbling. When the inclination angle is small, obviously the horizontal component will be much bigger. That's why the concrete slab opens. And when the inclination angle is greater, in this case, of course, the vertical component will be bigger, so the failure mode will be concrete crumbling. Here you can see the top surface of the specimens, that in case of small inclination angle, the concrete slab just opens, but in case of great inclination angle, the opening is much smaller. So here you can see the numerical models, and that the results are pretty similar to the experiments. In case of small inclination angles, the concrete slab opens and the failure mode will be slab opening, and in case of for example 60 degrees of inclination angle, the failure mode will be concrete crumbling, and the opening will be much smaller compared to the 30-degree specimens. Here you can see the force displacement curves for the experiments. About the curves, you can see that the shape of them are similar to each other, so the change in the parameters, like the changes in the bending depth or the inclination angle or the plate width, are not affects directly the shape of the curves. The initial stiffness is roughly the same, and of course you can see that all of the curves are really ductile. Next to the figure, you can see the specimens with the load capacities, both from the experiments and from the numerical investigations. And at the last column, you can see the difference between the test and the finite element model. They are pretty close to each other. According to the results of both the tests and the finite element models, we can say that in average, changes in embedding depth from 100 to 125 millimeters results 6 50% increase in load capacity from 100 to 150 millimeters. It leads to 18% of load capacity increase. The change in the plate width from 200 to 100 millimeters results in a 50% load capacity increase, and the change in inclination angle from 30 to 45 degrees results in 80%, and from 30 to 60 degrees results in 180% load capacity increase. Of course, the biggest influence, of course, the inclination angle has the biggest influence on the load capacity, because it directly affects the failure mode, as we have seen in the previous slides. So in conclusion, the inclination angle and the plate width do not affect the force displacement, the shape of the force displacement curves, and the inertial stiffness is roughly the same. The push-out specimen's behavior is really ductile. The inclination angle closer to the vertical. In case of the inclination angle is closer to vertical, the failure mode will be slab opening. In case of inclination angle closer to horizontal, the failure mode will be concrete crumbling. Bigger embedding depth, greater inclination angle, and smaller plate width will result in higher ultimate shear capacities, and the Athena software provides a good approximation of the push-out test results, so a parameter analysis can be performed on the verified model. Thank you for your attention.